All right, this is the 5th FRQ on the 2017 BC exam. So the first thing they want us to do is find the slope of the tangent line at 3. So that's pretty easy. We've got the function. You can use the quotient rule, or you could take this, bring it up to the top with an exponent of -1 for the whole thing, and you could use the chain rule. It's up to you. I'm going to go ahead and use the quotient rule because my guess is that's what most people would do. So we're going to say low d high minus high d low divided by low squared. Because that's times 0, that's nothing. So now I can go ahead and do f prime of 3, and I have -3, 4 times 3 minus 7, 2 times 3 squared, 7 times 3 plus 5. Two times 9, -3 times 5, 18 minus 21 is -3. -3 plus 5 is 2. Okay, so -15 fourths. You can leave it here, you can leave it there. Not a bad idea to leave it here if you're at all unsure about your computations. All right, part B says find the x value of each critical point on the interval from 1 to 2.5, and then classify each critical point as relative maximum, minimum, neither, and justify. So what I did is I said critical points happen when the derivative is 0 and when the derivative is undefined. And so when the derivative is 0, that's going to be when -3 times 4x minus 7 equals 0, which is going to happen at 7/4. The derivative, so that's the top of the fraction, right? The numerator of the fraction, because the denominator is a fraction, so the numerator equaling 0 is what would make the whole thing equal 0. The denominator equaling 0 is what would make it undefined, and so that would be 2x squared minus 7x plus 5 squared equaling 0. So I'm going to go ahead and factor this. It's a slide divide problem. That's how I always do it, is slide divide, but you might do guess and check or whatever. So 2 times 5 is 10, -7. So the two numbers that multiply to 10 but add to -7 are -5 and -2. And then because we slid the 2 over to the 5 to get the 10, I'm going to go ahead and divide by 2 and divide by 2. So I've got 2x minus 5 for this one, and x minus 1 for that one. And so x equals 5/2, x equals 1, and if you can tell, those are actually the ends of the interval, so we don't have to use those at all because it's an open interval, which means they're not including their endpoints. So that was fun to do that work unnecessarily. Okay, so a number that's between 1 and 7/4, that's 1.75, so maybe 1.5 I could plug in. A number that's between 1.75 and 2.5 would be like 2. So if I think about the derivative, the bottom is squared. So no matter what I plug in on the bottom, it's going to be a positive answer. So that means that all that matters is what I plug into the top. So here I'm going to say -3, and then I've got 4 times 1.5 minus 7 over positive. And over here I've got 4 times 2 minus 7 over a positive number. 4 times 1.5 is 6. 6 minus 7 is -1. So I've got -3 times -1 is positive, so that's a positive. 8 minus 7 is +1, -3 times +1 is a negative, and so this is a relative max at x equals 7/4 because f prime switches from positive to negative there. All right. Part C says to use this partial fraction decomposition that they gave us to evaluate the integral from 5 to infinity of f of x dx, or to show that the integral diverges. So we've got the integral from 5 to infinity, 2 over 2x minus 5, 1 over x minus 1 dx. And so what I did, since I recognized this needed u substitution, this one didn't, I went ahead and just split them up. So I've got u is 2x minus 5, du is 2 dx, and kind of fun, this one actually has the 2. So we're going to integrate 1 over u, and then 1 over x minus 1. I am not going to stick the 5 to infinity here because that's not in terms of u, that's in terms of x. I'll go ahead and leave this here. I'm going to actually, for most of the time, I do whatever problem in terms of u. However, from previous experience, I know that sometimes when there's multiple fractions like this, they do interact with each other, where if I did them separately, I wouldn't see something that if I do them together, I will. So I'm going to keep doing the problem, and then I will go back and explain why I did not evaluate this one separately from this one. Okay, so integral of 1 over u is ln u. So I've got ln of 2x minus 5. All right, and then I'm subtracting off ln of x minus 1, subtracting off ln of x minus 1, and then that whole thing is being evaluated from 5 to infinity. So I have, and at some point we do need to write down that limit notation because of the infinity, and I can't remember exactly where we need to put it, so I'll go ahead and do it here. I'll say the limit as c goes to infinity. And I'll go ahead and put c right here. Okay. So if you guys recall the property of logs, anytime you have two logs and you're subtracting them, that's actually a division problem. So I've got the limit as c goes to infinity. I'm actually not going to need this anymore. ln, and then I've got 2x minus 5 over x minus 1, and that's going to be evaluated from 5 to c. So this is actually the reason, this right here, this is not your final answer, we're not done yet, but this is the reason that I did not evaluate these separately. Because if I had done it separately, I would have been like plugging a number in, plugging an infinity in, and I would have been like, okay, that diverges. If I had plugged in a number, plugged in infinity, I would have thought this diverges. But when you do this together, then you can see that the limit as c approaches infinity of ln, we've got 2c minus 5 over c minus 1, and then we've got, so we're subtracting off the bigger number, and then we've got 2 times 5 minus 5 over 5 minus 1. You can actually see that because you've got the -5 and the -1 that are so small that they're unnecessary, then you've got your infinities of the same size. This is actually ln 2. It's actually not divergent. And then over here, we've got 10 minus 5 is 5 over 4, so minus ln 5/4. So this is actually a convergent problem. It actually converges to a specific value, whereas if we had done the two pieces separately, we wouldn't have seen that. So typically, when you break up integrals and you do one minus another, you can just do the sum of one minus the sum of the other, and you'll be fine. But you have to be careful in situations like this to watch out for that, because that would have been an easy mistake to make. So you probably can't leave it right here because of the c's. But once you get this down to here, this you should have been able to leave there. And we can keep going. We can say this is subtraction, so it's division. So we have 2 divided by 5/4, which is actually, you'd flip the 5/4 up to 4/5. So that's actually ln of 8/5, which is the final answer. But you should have been able to leave it a few steps back and still have been okay. All right, so that was part C. Part D is asking you to find whether or not that series is convergent or divergent. Now, we basically just did the integral test. And with the integral test, we found that it converged to a value, which means that the series itself is convergent, but we have to state the conditions, and then we have to say that we use the integral test before we make that conclusion. So we're going to say first that f of x, actually, I'll go ahead and write this. So we'll say n equals 5 to infinity, and then it was 3 over 2n squared minus 5n plus, nope, 7n plus 5. So we'll say let that was supposed to be a t. Let f of x equal 3 over 2x squared minus 7x plus 5. We're going to say f of x is positive, decreasing, and continuous. So if you remember, those were the three things you had to have for the integral test to work on the interval from 5 to infinity. Okay, and now that we've said that, then we can say 5 to infinity f of x dx converges, therefore by the integral test, the sum also converges.